My name is Adiv Paradise. I'm a fourth-year PhD student at the Center for Planetary Sciences at the University of Toronto with Kristen Manu. And I want to quickly revisit the habitable zone. Here I have to thank Thaddeus for introducing the strike zone idea. I saved him like 3 slides. So we have the inner and the outer edge, and their positions can vary based on other factors. So I think it's more useful maybe to think about a warm edge and a cold edge, rather than just inner and outer. The warm edge we can think of as any combination of things like having high insolation, strong greenhouse effect, being really bad at cooling, and the cold edge, some combination of having low insolation, a weak greenhouse effect, and being really good at cooling. So most generally at the warm edge you have strong forcing, and at the cold edge you have weak forcing. I'm particularly interested in the cold edge, particularly in snowball planets. To quickly recap from this morning, snowballs, they're a climate that happened a few times on Earth. They're really, really cold. They're characterized generally by sea ice all the way to the equator, though there's some disagreement on how total that coverage is. And we think of them as having glaciers everywhere, being really, really icy. Definitely not a temperate place. My work, however, suggests that that's maybe not necessarily the case. We'll get into that a bit later. Snowballs are in a bifurcation state. So there's 2 stable branches, the snowball branch and the temperate branch. We often define this in terms of insolation. We can also do it in terms of CO2 partial pressure, or more generally just the radiative forcing. Now I use, in contrast to some other people here, a model called PlaSim. PlaSim is developed at Hamburg. It's open source, and I won't get too much in the details of how it works for the sake of time. But basically it's just complex enough that you can model a wide range of climates that are vaguely Earth-like, but do them relatively fast. So it trades off accuracy for efficiency. So we can do 1 year of climate in about 45 seconds on 8 CPUs. So not in the same weight class as Rocky 3D, but use them for different things. So my interest is particularly on warm snowballs. So here on the right I've plotted snowball bifurcations for various parameters. Every dot is a PlaSim model run to equilibrium a couple decades to a couple centuries. And we do warm snowballs because, as you heard earlier with the carbon cycle, we assume that volcanoes are going to keep outgassing CO2 even on the snowball branch. We assume that snowballs don't have a whole lot of weathering to counter that, so you should move up that snowball branch towards that warm end. So the warm snowballs are kind of an end group for the cold edge of the habitable zone. So here I've plotted the average surface temperature for a range of climates across insolation and PCO2 at the warm edge of the snowball branch. You can see the transition up out of snowball is the red. But here now I've plotted the maximum surface temperature for those same models. And you can see that snowballs are still everything below this green line, but now we have this slice of parameter space where the maximum temperature is above freezing. So that's kind of odd. So we take a closer look. We look at an illustrative example, say 1355 watts per square meter, a little bit further than the Earth, 5 millibars of PCO2. Average annual temperature is still below freezing everywhere. If we go zoom in closer and look at seasonal data, January is still cold everywhere. But when we go to July, we have all of a sudden these large land areas where the temperature is rather warm, up to maybe 20 Celsius in some places. So what we have here is we have a climate that has temperate regions on land in the summer. So this is seasonally habitable. Now I'm from Minnesota originally, so that's not too outlandish an idea for me. But it's still worthwhile looking at what's actually going on here. So I think the key factor here is that we basically have a collapse of the snowpack in the northern hemisphere. And you can see that there are dry regions here, and even in February in the winter, even though you get some snow back, you still have these dry regions. We think this is probably a relatively robust result. You heard from Sunny that if you look at paleo Earth and snowball, you get dry regions that don't have ice. If you look at the last ice age, large parts of Russia stayed dry. So it seems to be fairly difficult to cover all of the land surface with lots and lots of snow and ice. That's important because bare ground has a lower albedo than ice, and that's going to have a strong influence when you add a lot of shortwave forcing. So in June and in the spring, as you're warming up into northern hemispheric summer, the sun's getting higher in the sky, so shortwave forcing is becoming very important. And then in the fall, as you're moving out of it, shortwave becomes less important. And it's not really a coincidence that that also happens to be correlates with those temperature trends in the northern hemisphere. We can see this as well if we look at how this varies throughout the habitable zone. As you go to lower insolation, you have more forcing from CO2. CO2 gets more important. Insulation's going down, so shortwave is getting less important. And the amount of temperate land area is also going down. So as you're losing that shortwave forcing, you're also losing the temperate areas. And then if we look at the temperatures of those temperate areas, we find that not only are they getting smaller, they're also getting colder. So the key mechanism here is that if you combine bare ground with a low albedo with a lot of shortwave forcing at high insolation, you're going to get warm ground, even if the rest of the planet is frozen. So we can consider a simplifying case, because if that's the case, what if we consider a planet with no seasons, zero obliquity, and we just make a rectangular flat supercontinent and stick it on the equator? So that therefore you have just the sun's always in the same spot, and at the equator is where the sun's at solar noon year-round. So when we do this, we get basically the same result. We have a large region of land that has temperatures above freezing, and everywhere else is mostly in Snowball. But note that this is the annual average temperature, no longer seasonal. So now we have a planet that has a persistent temperate region on land while in Snowball, which means that this would be an example of a Snowball climate that I would argue is unambiguously habitable on its land surface. So this challenges our traditional view of snowballs as being sort of a problem for surface habitability. So okay, even if you buy that, how likely are these things actually? This is a narrow slice of the parameter space, so maybe most planets won't ever get to this. Well, the key here is that we think that volcanoes will continue to outgas CO2 during Snowball, and in this area where temperatures below freezing everywhere, you're not really going to have any weathering to balance that. So the Snowball climates that are colder than this should move up into this temperate Snowball region. And at that point, we remember from earlier this morning that continental weathering requires CO2, requires liquid rainfall, temperatures above freezing so you can have that water delivering the CO2 into the rock, and you need to have exposed land. Well, here we have all four of these things. So we can go ahead and compute what that weathering might be like in these climates, and we find that as you move up into this temperate Snowball regime, you start to have some weathering that can maybe balance a little bit of outgassing. And if we look at the spatial data and compute that weathering, then we find that in some places it's rather vigorous, up to 10 times as strong as the average weathering that we think on Earth. So we can measure that weathering for all of these models at the limit of the Snowball branch and look at that across the habitable zone. We can compare that to the weathering that we see in the temperate branch. So here the black dotted line is the minimum weathering that we see on the temperate branch, and the blue dots are the maximum weathering that we see in these Snowball models at the warm end of the Snowball branch. And we can use this to make a stability diagram. So above the black dotted line, you can have a stable temperate climate where weathering balances outgassing, and below the blue dots, you can have a stable Snowball climate where weathering balances outgassing. And the key here, so that you can see that there are some cases where snowballs could be stable. And the key here is that these are planets that have low outgassing rates. In this particular case, with Earth continents, no more than 10% of Earth outgassing. So I'm going to finish up here with some keys and caveats. The key mechanisms for this are that high insolation snowballs seem to be qualitatively different from low insolation snowballs, in that it seems to be relatively easy to end up in this regime where you have these large temperate areas. And that's the consequence of a combination of strong shortwave forcing, large areas of bare soil, a buildup of CO2 leading to these temperate areas, and that permits continental weathering that can be enough on low outgassing planets to trap you in Snowball and make this a stable climate. A sample of the caveats, because of course there are many, are that the ice sheet dynamics are going to matter, of course. You have to get that bare ground. So depending on how you model your ice sheet evolution, how you model your snowpack, maybe that can change the picture. If your ground is at high elevation or it has a high albedo, it's going to be harder for it to cool even if you lose that snowpack. And if you have very slow erosion, then you could, with that vigorous weathering, quickly run out of rock to weather. And so that could limit the weathering that you can do in Snowball, and that would limit the stability of this case. And I'll pause there for questions.
I'm going to ask the first one.
Okay.
So your bare ground areas, are you actually getting liquid rainfall to do that weathering? I would have maybe naively assumed you'd have more like Antarctic dry valley situations.
Yeah, actually I have some plots, I think. Yeah, so if we look at precipitation, maybe the key plot here is this one on the bottom left, and that's precipitation that happens to fall as liquid rain when the ground is also above freezing. And so you can see that you do have some. It's not a ton, but there is some. The main driver seems to be the temperatures and the high CO2 levels that permit that weathering.
Hey, great talk. I love the idea of using simpler models, but I noticed that you're using T21, and at T21 and Earth's rotation rate, you are not resolving mid-latitude eddies. Do you think that impacts your results, especially when it comes to precipitation?
That's certainly possible. The main way that would impact that is if you include the mid-latitude eddies, if that makes it easier to move water away from those bare ground areas, and that could potentially affect the amount of weathering that you can do. I think the phenomenological result of having these open areas would still stand. But I think whether or not there's enough weathering to make it stable, I think it's definitely sort of the most uncertain part of this whole picture. Sure.
Yeah, so really interesting result. I was wondering if you could say some words about how PlaSim is handling clouds, and how big an uncertainty you think that's going to be in this result.
Yeah, so for this, I'll go back to the plot of the shorewave forcing because you can kind of see the imprint of the clouds there. Here we go. So in the shortwave down, you can kind of see where there's less shortwave down. That's kind of where the clouds are. So the clouds are produced sort of diagnostically. So PlaSim will compute convection. It will compute water transport. And that says, okay, well, where the relative humidity exceeds a certain threshold, that will start producing clouds and start precipitating rain out. And that will compute some re-evaporation. So I don't want to say that PlaSim has the right cloud model, because I know that there are many disagreements in GCMs about how to do clouds. I would say that if you had more cloud cover, it might make it harder to warm up because you're limiting the amount of shortwave radiation getting to the ground. But you also have less evaporation in a snowball than you do in a temperate climate. So I would imagine that would make it a little bit harder to form clouds in the first place. So you're limiting the amount of water making it up into the atmosphere. I think possibly the reason you see clouds in this case is because you started to melt some water and add some water vapor.
Hi, I was wondering about your distribution of continents and whether that has any effect or if it's just the total fraction of the surface that is land.
Yeah, so that has a huge effect, I think. So here I've got Earth continents, and you can see that's basically where the bare ground opens up. And here that's okay because we also have Earth-like obliquity. So even though this land is at relatively moderate to high latitudes, it gets strong sunlight in the summer. If you had poleward land but low obliquity, then that land wouldn't really get to high enough insolation unless the planet was closer in. And you saw with the supercontinent case, the more land you pack at higher insolation, the easier it is to get temperate land area.